Hello, in this lecture we will answer on two questions. The first question is to find out the area of the semicircle, this semicircle that is inscribed inside a quarter circle, and the second question is to find out the size of this angle theta, that is angle of the right triangle ABC. So we'll start with the first question. We'll answer on this question. We'll answer on both questions in two different methods. So we'll start with the first method. In this drawing we have this quarter circle. The radius of the quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. So we will define the center of the semicircle as point C, and I will present to you a new rule that is actually rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I will read rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? If we have this circle and we have also tangent AB to this circle, here this tangent AB is tangent to this circle at this point, that is point M. Point M is the point of tendency of tangent AB with this circle. Point of tendency and the center of this circle is at point O, this point, and here OM is the radius of this circle. We define it as R. So here we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to this radius. In this case, the tangent AB will be perpendicular to the radius MO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So again, whenever a radius is drawn to the point of tendency, like in this drawing, then the tangent will be perpendicular to that radius. In this case, AB will be perpendicular to MO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so we actually can implement rule number 1 in our drawing. Here, this point will be A, B, O, C, A, B. This point will be defined as C. This point will be defined as F, and this point will be defined as G. Here we will connect point C and B together by a straight line. CB is the radius of the semicircle because of the fact that it starts from point C. C is the center of the semicircle. Point C is the center of the semicircle. So line segment CB starts from point C, that is the center of the semicircle, and ends at point B, that is the point of the semicircle itself. Therefore, it is the radius of the semicircle, so we will define the radius of the semicircle as R. Therefore, BC will be equal to R. And here we have the tangent, we have the radius CB that is drawn to the point of tendency, that is to say, it is drawn to point B, that is the point of tendency of tangent AD with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent AD will be perpendicular to the radius BC. So AD is perpendicular to BC. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, from the center of the semicircle, we will draw the radius to point D, that is the point of tendency of tangent D edge. Tangent D edge is tangent to the semicircle at point D. D is the point of tendency, and we have here the radius CD. The radius CD, it is drawn to the point of tendency, that is to say, it is drawn to point D, that is the point of tendency of tangent DH with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent DH will be perpendicular to the radius DC. That is to say, this angle will be equal to 90 degrees, and this angle will be equal to 90 degrees according to rule number 1. And here we have angle BOD, or actually, because of the fact that AO edge is a quarter circle, this angle must be equal to 90 degrees. Okay, I'll repeat again, because of the fact that AO edge is a quarter circle, angle AO edge must be equal to 90 degrees. So inside quadrilateral BCOD, we have 3 right angles. inside quadrilateral BCOD. We have three right angles. The sum of three right angles is 90 times 3 is 270 degrees. 270 degrees plus the size of the fourth angle of quadrilateral BCOD, that is actually angle BCD, this angle. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We'll subtract 270 degrees from this equation, and we get that the angle, the missing angle BCD, is equal to 360 degrees minus 270 degrees. It is 90 degrees. Okay, so the missing angle is a right angle. It is equal to 90 degrees. Therefore, quadrilateral BCOD has four right angles, and any quadrilateral that has four right angles must be at least a rectangle, if not a square. So, quadrilateral BCOD is a rectangle. Okay? Quadrilateral BCOD is a rectangle. And we have the rule that, this will be rule number 2, that the opposite sides of a rectangle are equal to each other. I'll read rule number 2 again. According to rule number 2, the opposite sides of a rectangle are equal to each other. So here, in rectangle BCOD, the opposite sides are equal to each other. That is to say, BC equals to OD. According to rule number 2, BC equals to OD. According to rule number 2. But BC equals to R, it is the radius of the semicircle, so we can write here that BC equals to R, and from this equation R equals to BC equals to OD, we will derive that OD is also equals to R. OD is also equals to R. So here, we can write here that OD is equals to R. Likewise, for the same reason, CD will be equal to BO. According to rule number 2, that the opposite sides of a rectangle are equal to each other. In rectangle BCOD, CD must be equal to BO. CD must be equal to BO according to rule number 2, that the opposite sides of a rectangle are equal to each other. But we know that CD equals to R, it is the radius of the semicircle. CD equals to R, and from this equation R equals to CD equals to BO, we will derive that BO is also equals to R. BO is also equals to R. So we can write here that BO equals to R. Actually, we found out that all the sides of quadrilateral BCOD are equal to each other, they are all equal to R, and it has also 4 right angles, therefore quadrilateral BCOD is not a square but a rectangle. Okay, quadrilateral BCOD is a square. Okay. In the next step, we will join together points C and O by a straight line. CO is the diagonal of square AB. CO is the diagonal of square BCOD. We will find out the size of the diagonal CO by implementing the Pythagoras theorem on the right triangle, triangle ODC. In the right triangle, triangle ODC, or COD, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the green triangle COD by PT, PT is the progression for Pythagoras theorem, we will get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say OC square equals to CD square plus OD square. So in the right triangle, right green triangle, triangle COD, according to the Pythagoras theorem, OC square equals to CD square plus OD square. OC is the missing variable, so OC square, we will leave it as it is, and it is equal to CD square. CD equals to R, so CD square will be equal to R square plus OD square. OD equals to R, so OD square will be also equal to R square. So in conclusion, we found out that OC square, the diagonal of the square, it is equal to R square plus R square, that is 2R square. Here we take a root out of this equation and we will get that the diagonal OC of the square, it is equal to square root of 2 times R. OC equals to square root of 2 times R. OC equals to square root of 2 times R. In the next step, we will extend diagonal OC until it touches the circle at this point. And we will define the touching point of the extended OC in the circle as point S. So what is the length of line segment SC? The length of line segment SC, it will be equal SC. From the drawing you can see that SC or CS, it is equal to OS minus OC. OS minus OC. So SC, line segment SC, will be equal to OS. OS is the radius of the quarter circle, because it starts from the center of the quarter circle, that is to say from point O, and ends at point A, that is the point on the quarter circle itself. Therefore, it is the radius of the quarter circle, that is to say it equals to 3 units. So SC equals to OS, that is 3, minus OC. We just right now found out that the length of the diagonal OC of square BCOD equals to square root of 2 times R. So OC equals to square root of 2 times R. In conclusion, we found out that the length of line segment SC equals to 3 minus square root of 2R. Okay, SC equals to 3 minus square root of 2R. I write it down here. SC equals to 3 minus square root of 2R. Okay, in the next step, we will complete the quarter circle to a circle. Okay, we complete the quarter circle to a circle. So here we have this. So this is the circle that we completed from the quarter circle. In the next step, we will extend the diagonal OC until it touches the circle at this point. We will extend the diagonal CO by a straight line until it touches the circle. At this point, we will define the touching point of the extended CO and the circle is point M. So what is the value of line segment MO or OM? Line segment OM starts from the center of the circle, that is to say from point O, and ends at point M, that is the point of the circle itself. And this is exactly the radius, the definition of a radius. That is to say, OM, it is the radius of the quarter circle and also the radius of the circle itself, that is equal to 3 units according to what is given us the question. In conclusion, we found out that MO is the radius of the circle and the quarter circle, that is actually equals to 3 units. And in the next step, I will present to you a new rule number 3. Rule number 3 relates to 2 chords inside the circle that intersect with each other. Okay, so whenever 2 chords intersect with each other, this will be rule number 3. If two chords intersect with each other inside the circle, this is chord AB, and chord AB intersects with chord CD. This is called CD. Those 2 chords intersect with each other at this point. This is the intersection point. We'll define the intersection point as point O. Then, whenever 2 chords intersect with each other inside the circle, then the following formula is true, that AO times OB is equal to CO times OD. Okay? I repeat again. Whenever two chords intersect with each other inside the circle, then the following relationship exists between their parts. AO times OB equals to CO times OD. We can implement rule number 3 in our drawing. In our drawing, we have two chords that intersect with each other. We have chord MS or chord SM that intersects with chord FG. Chord MS intersects with chord FG, and the intersection point is this point C. Okay? Therefore, according to rule number 3, we'll get that MS times, it is actually MC, this is point C, MC times CS is equal to FC times CG. I repeat again. Chord MS intersects with chord FG, and the intersection point is at point C. Therefore, according to rule number 3, we will get that MC times CS equals to FC times CG. Okay? This is true according to rule number 3. Okay? What is the value of line segment MC? The value of line segment MC, it is very easy to see from the drawing that line segment MC, this line segment, it is equal to 3 plus square root of 2r. Again, MC equals to 3 plus square root of 2r. Okay? MC equals to 3 plus square root of 2r times CS. What is the value of CS? We have already found out that CS equals to 3 minus square root of 2r. 3 minus square root of 2r, and it is equal to FC. What is the value of line segment FC? C is the center of the semicircle. F is a point on the semicircle itself. Again, C is the point on the semicircle itself. And this is exactly the definition of a radius. That is to say, CF, it is equal to the radius of the semicircle. That is to say, it is equal to R. Likewise, line segment CG. C is the center of the semicircle. G is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, it is the radius of the semicircle. That means that it equals to R. Okay, so we found out that CG equals to R, and FC is also equals to R. In conclusion, we found out that 3 plus square root of 2R times 3 minus square root of 2R equals to R times R, that is actually R squared. We will calculate the value of this expression, 3 plus square root of 2r times 3 minus square root of 2r, by the algebraic identity that states that a plus b times a minus b, it is equal to a squared minus b squared. Okay, in our specific expression, a is equals to 3 and b is equals to square root of 2r. And according to the algebraic identity, a plus b times a minus b equals to a squared minus b squared. That is to say, in our specific expression, it will be equal to a squared. A is 3, so a squared is 9, minus b squared. B is square root of 2r. Square root of 2r squared equals to square root of 2 squared, that is 2, times r squared. So in conclusion, we found out that this expression, 3 times square root of 2r times 3 minus square root of 2r equals to 9 minus 2r squared. And this is equal to r squared. Here we will add 2r squared to this equation, and we will get that 9 equals to r squared plus 2r squared is 3r squared. We will divide this equation by 3, and we will get that r squared equals to 9 over 3 is 3. So we found out that r squared equals to 3. And what is the area of this semicircle? The area of a circle is pi r squared. Therefore, the area of the semicircle will be half of it. That is to say, the area of this semicircle will be equal to pi r squared. Pi r squared, area of semicircle. Area of semicircle, it is equal to pi r squared over 2, of course. Pi r squared is the area of a circle, and when we divide it by 2, we'll get the area of the semicircle. So pi r squared equals to 3. We substitute r squared by 3 over 2. That is to say, the area of the semicircle equals to 3 pi over 2 square units, or in terms of numbers, it equals to 4.71 square units. Okay, so we found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equals to 4.71 square units. Okay, the area of this semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this semicircle according to the second method. We will use all the things that we found out in this method in the second method. So this will be the second method. The center of the semicircle is at this point C. We have already found out that we have here a square. This is point A, B O D. BCOD is a square, according to what we have already found out in the first method. In the next step, we will join here. This point is point F, and this point is point G. We will join points F and O together by a straight line. What is the size of the length of line segment OF? O is the center of the quarter circle, and F is a point on the quarter circle itself, and this is exactly the definition of the radius. That is to say, OF is the radius of the quarter circle, that is equal to 3 units. So OF equals to 3 units. Likewise, we will join together points O and G by a straight line. OG, what is the length of line segment OG? O is the center of the quarter circle. G is a point of the quarter circle itself. And this is exactly the definition of a radius, that is to say OG is the radius of the quarter circle, that is equal to 3 units. Therefore, triangle FOG is an isosceles triangle, because side OF equals to side OG equals to 3 units. And the base of the isosceles triangle, triangle OFG, will be FC. We have already found out that FC in the first method, it is equal to the radius of the semicircle, that is to say it is equal to R, and CG is also the radius of the semicircle, that is equal also to R. Okay? We will join points O and C together by a straight line. OC is the diagonal of the square, that is equal to square root of 2R. We already found out in the first method that diagonal of the square equals to square root of 2R. But OC is not only the diagonal of a square, it is actually the median to the base of the isosceles triangle, triangle FOC. Why OC is the median to the base? First of all, when OF equals to OG, we are talking about an isosceles triangle, that is to say triangle OFG is an isosceles triangle, and the base of the this isosceles triangle must be FG. So the base is FG, and the median to the base is OC. Why OC is the median of base? Why OC is the median to the base FG? Because of the fact that OC bisects the base into 2 equal parts. That is to say FC equals to CG equals to R. Okay, so I will copy again the right triangle, triangle FOG in the new page, and I will present to you a new rule. This is actually rule number 4. So we have the isosceles triangle, triangle FGO, I'll repeat again. Here, this is the isosceles triangle FOG. The base of the triangle is FG, and the median to the base, it is actually equals to OC. OC is the median to the base FG. I'll repeat again. We have here an isosceles triangle OFG. Triangle OFG is an isosceles triangle. The base of the isosceles triangle FG, the base of the isosceles triangle is FG. FG is the base of the isosceles triangle OFG, and OC is the median to the base. OC is the median to the base. To the base FG. And we have also rule number 4. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. I'll repeat on rule number 1 again. On rule number 4. I'll repeat on rule number 4 again. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So in the drawing we have the median OC. This is the median to the base. So the median OC to the base, according to rule number 4, is perpendicular to the base FG. This is the base of the isosceles triangle OFG, and according to rule number 4, the median OC to the base FG is perpendicular to the base. So that is to say, OC is perpendicular to FG. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? So, we'll implement rule number 4 in our drawing. this is actually the implementation, because here this angle will be equal to 90 degrees. We have the median OC to the base FG, and the median to the base in this isosceles triangle is perpendicular to the base according to rule number 4. That is to say, OC is perpendicular to FG. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay. In the next step, we will implement the Pythagoras theorem on the green right triangle, triangle OCF. Okay. So this is the right triangle, triangle OCF. We will implement the Pythagoras theorem on the right triangle, triangle OCF. We know that FC equals to R. OC is the diagonal of the square that is equals to square root of 2R. So, in the right triangle, triangle OCF, we will get that according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I copy it here again. We have the right triangle, triangle OCF. We know that OFC equals to R. OF is the radius of the quarter circle, that is to say it is equal to 3 units. And OC is the diagonal of the square that is equal to square root of 2R. So this is the right triangle, triangle OCF. In the right triangle, triangle OCF, by PT is by Pythagoras theorem, by PT, we get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right green triangle. That is to say, the square of the hypotenuse is OF square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to FC square plus OC square. OF equals to 3, so OF square is 3 squared, it is 9, and it is equal to FC square. FC equals to R, so FC square is R square plus OC square. OC equals to square root of 2R. Therefore, OC square equals to square root of 2R square. Square root of 2 is 2 times R square. And the square of R is R square. In conclusion, we found out that 9 equals to R plus 2R square. R plus 2R square is 3R square, or 9 equals to 3R square. We divide this equation by 3, and we get that R square equals to 3. R square equals to 3. And I've already explained to you that the area of the semicircle it is equal to pi R square over 2. That is to say, it is pi. R square is 3 over 2. That is to say, it is equal to 3 pi over 2 square units, or in terms of numbers, it is equal to 3.71 square units. Okay? So the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. Okay? We finished with the first question. In the next step, I will present to you the second question, and we will use two different methods in order to solve the second question. Okay? In the drawing, we have the right triangle, triangle ABC. Triangle ABC is the right triangle because angle ABC equals to 90 degrees. We also know that AE equals to EC, and we know that DE is perpendicular to AC. That is to say, this angle DEA equals to 90 degrees, and angle DEC, this angle equals to 90 degrees also. And we also know that line segment DE is equal to 2 units. Side BC of the right triangle, triangle ABC, equals to 6 units. And we want to find out the size of this angle theta, that is actually also angle BAC. Angle BAC equals to theta. We want to find out the size of angle BAC that is equal to theta. So, first of all, we will draw a perpendicular from point E on BC. So this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We've defined the touching point of the perpendicular from point E and BC as F. We will define angle BECA as alpha. Angle BCA, this angle, it is equal to alpha according to our definition, but this angle is one angle of the right triangle, triangle ABC. And we already know that in this right triangle we have one angle that is equal to 90 degrees. This angle is equal to angle theta, that is the angle that we are looking for. So if in the right triangle ABC this angle equals to theta, then this angle must be equal to 90 degrees minus theta. In order to complete the sum of the angles in the right triangle ABC, 280 degrees, this angle must be equal to 90 degrees. Therefore, we can write down that here that alpha equals to 90 degrees minus theta. Alpha equals to 90 degrees minus theta. Here 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the reason that this angle must be equal to 90 degrees minus theta. Okay, so we actually know that alpha equals to 90 degrees minus theta. Here we will add to this equation theta, and we will subtract alpha, and we will get that theta equals to 90 degrees minus alpha. We get theta equals to 90 degrees minus alpha. So here in the right triangle FEC, this angle equals to alpha. So this angle must be equal to 90 degrees minus alpha. But 90 degrees minus alpha equals to theta. Okay, 90 degrees minus alpha equals to theta. It is given us in the question that angle DEC equals to 90 degrees. Angle DEC equals to 90 degrees according to what is given us in the question. What is given us in the question? Angle DEC equals to 90 degrees. So angle DEC minus this angle, that is angle FEC, will give us the value of this angle that is actually angle DFE. I repeat again, angle DEC minus angle FEC will give us the value of angle DEF, this angle. So angle DEF will be equal to angle DEC, that is 90 degrees according to what is given us the question, minus angle FEC. Angle FEC equals to 90 degrees minus alpha. So angle DEF, the missing angle, will be equal to 90 degrees minus 90 degrees, that is 0, minus alpha is plus alpha. We found out that the missing angle DEF equals to alpha. Here this angle equals to alpha. In the right triangle DEF, if this angle equals to alpha, then this angle must be equal to 90 degrees minus alpha. Okay? In order to complete the sum of the angles in this right triangle to 180 degrees, if this angle equals to alpha, this angle must be equal to 90 degrees minus alpha. But 90 degrees minus alpha, it is theta. So we can write down that this angle equals to theta, that is 90 degrees minus alpha. Okay, in the next step, we will define side DF of the right triangle DEF as x. We will define side EF of this right triangle DEF as y. We will define line segment AE as A. And because of the fact that AE equals to EC, this is given us in the question, then EC must be also equal to A. And in the next step, we will prove that the right the right big triangle ABC is similar to the right small triangle FEC. Write it down, triangle ABC, the right big triangle. We will prove that it is similar to the right small triangle FEC. So why those two right triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to 90 degrees, so we can write down that angle ABC in triangle ABC is equal to angle EFC in triangle EFC, and both those two angles are equal to 90 degrees, they are right angles. Angle ABC equals to angle EFC equals to 90 degrees. We also know that those two angles are also equal to each other. They are both equal to theta. Because here 90 degrees minus alpha equals to theta. So both those two angles, they are equal to each other, they are equal to theta. So we can write down that angle BAC of triangle ABC is equal to angle FEC of triangle EFC, and both angles are equal to theta. Okay. Angle BAC equals to angle FEC, and both those angles are equal to theta. And finally, here, this is a common angle. It belongs to both triangles. So we actually can write down that this angle equals to itself. Angle alpha belongs to triangle EFC, as you can see, and angle alpha is also belongs to triangle ABC. So we can write down that angle BCA, in this way, I will emphasize that it belongs to triangle ABC. Angle BCA is equal to angle FCE. This also belongs to triangle FCE. And this angle equals to alpha. It is a common angle. So actually, angle BCA equals to angle FCE equals to alpha. It's a common angle that belongs to both triangles. So all three angles of the right triangle ABC can go into all three angles of the right triangle FEC. Both those two angles, they are equal to each other, they are equal to theta. Both those two angles are equal to each other, they are equal to 90 degrees. And finally, this is a common angle that belongs to both triangles. Therefore, triangle ABC is similar to triangle EFC according to angle similarity rule. Triangle ABC is similar, this is the sign of similar, to triangle EFC according to angle similarity rule. Okay? And from the fact that triangle ABC is similar to triangle EFC, we will conclude, hence, therefore, hence, AB over AC in the right triangle ABC is equal to EF over EC in the right triangle EFC. I repeat again, from the fact that triangle ABC is similar to triangle EFC, we will conclude that AB over AC equals to EF over FC. So according to equation number 1, AB over AC, what is the length of AC? The length of AC, it is equal to A plus A, that is 2A, and it is equal to EF over FC. EF is Y, and EF is Y, and here FC it is EF over EC. I repeat again. Actually, AB over AC, it is equal to EF over EC. It is EF over EC, not FC but EC. Again, AB over AC equals to EF over AC. What is the value of EC? The value of EC is A. So we substitute EC by A. In conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. Here we have A on both sides of equation number 1, so A will get cancelled. And we left only with AB over 2 equals to Y. We'll multiply equation number 1 by 2, and we will get that AB equals to 2Y. According to equation number 1, AB equals to 2Y. So you can write here that AB equals to 2Y. If we focus on the right triangle, triangle EFD, in the right triangle, triangle EFD, we know that x squared plus y squared equals to 2 squared. Okay, x squared plus y squared equals to 2 squared. 2 squared is 4. So in conclusion, we found out that in the right triangle, triangle FED, according to equation number 2, x squared plus y squared equals to 4. In the next step, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle EFD, this triangle. So we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle EDF. Why those two right triangles are similar to each other? Why they are similar to each other? First of all, we know that those two angles are equal to each other, they are both equal to 90 degrees. So angle ABC in the right triangle, triangle ABC, is equal to angle EFD, and they are both equal to 90 degrees. Okay, I'll repeat again. Angle ABC in triangle ABC equals to angle EFD in triangle FED, and they are both equal to 90 degrees. In addition, those two angles, they are both equal to theta, therefore they are equal to each other. Those two angles, they are both equal to theta, therefore they are equal to each other. So angle BAC is equal to angle EDF, this angle, and they are both equal to theta. I will repeat again. Angle BAC equals to angle DF equals to theta. And finally, those two angles, they are both equal to alpha, therefore they are equal to each other. So actually, angle ACB, the right big triangle ABC, this angle ACB is equal to angle DEF, this angle, and they are both equal to alpha. Okay, angle ACB in the right triangle ABC equals to angle DF in the right triangle DF, and they are both equal to alpha. So we prove that all the angles in triangle ABC can go into all the angles in triangle DF. Both those two angles they are equal to theta, both those two angles they are equal to alpha, and both those two angles they are equal to 90 degrees. So therefore, triangle ABC is similar to triangle EDF according to angle similarity rule. Triangle ABC is similar, this is the sign of similar, to the right triangle EDF according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will conclude hence that AB over BC, the right triangle ABC, AB over BC, here, AB over BC in the right triangle ABC is equal to DF over EF. In the right triangle is DF. I'll repeat again. From the fact that the right triangle ABC is similar to the right triangle EDF, we will conclude that AB over BC equals to DF over EF. AB equals to 2y, BC equals to 6, this is given us in the question, and it is equal to DF, DF equals to x according to our definition, and EF is also equal to y according to our definition. In conclusion, we found out that according to equation number 3, 2y over 6 equals to x over y. Here we will divide both the numerator and the denominator on this side of equation number 3 by 2. So 2y over 2 is y, and 6 over 2 is 3, so y over 3 equals to x over y. Here we'll cross multiply this equation number 3, and you will get that according to equation number 3, y squared equals to 3x. Y squared equals to 3x. But we have already found out that according to equation number 2, we have already found out that x squared plus y squared is equal to 4. Now we can substitute y squared in equation number 2 here by 3x, because y squared equals to 3x according to equation number 3. We will do it now, and we will get that according to equation number 2, x squared plus y squared is 3 squared, y squared is 3x, so we substitute y squared by 3x in equation number 2, and it is equal to 4. So in conclusion, we found out that according to equation number 2, x squared plus 3x equals to 4. We will subtract 4 from this equation number 2, and we will get that according to equation number 2, x squared plus 3x minus 4 equals to 0. So we have here a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, c are the coefficients of the quadratic equation, and x is the variable that we are looking for, and we will find out the value of x according to the following formula. X is equals to minus b plus minus square root of b squared minus 4 times ac over 2a in our specific quadratic equation. We know that the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we'll put the data inside the equation for x in order to find out the value of x. According to the special formula for x, you will get that x is equal to minus b, b is 3, so minus b is minus 3 plus minus square root of b squared, b is 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, and c is minus 4, over 2a. 2 times a is 1, 2 times 1 is 2, so we found out that actually x equals to minus 3 plus minus square root of minus 4 times minus 4 is plus 16, plus 16 plus 9 is plus 25 over 2. So we actually found out that x equals to minus 3 plus minus square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution, x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8. Minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. But here, from the drawing, you can see that x is the length of side df of the right triangle DDF, and x as a length, it must be a positive number. X is a length, therefore it must be a positive number. And therefore x1 can never be a negative number, therefore x1 is incorrect solution. We cancel this solution and we left only with the second solution. X2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, 2 over 2 is 1. So we found out that x2 equals to 1. So here we actually found out that x equals to 1. So I will copy the right triangle DEF in a new page and we will implement we'll do the cosine theta of this right triangle. Okay. So we have the right triangle DEF. This is the right triangle DEF that I copied from the original drawing. So here cosine theta in the right triangle EDF will be equal to DF over DE. Cosine theta equals to DF over DE. DF equals to 1. DE equals to 2. So in conclusion, we found out that cosine theta equals to 1 over 2. And when cosine theta equals to 1 over 2, it means that theta itself is equal to 60 degrees. So we found out that the answer to the question is that the size of angle theta is equal to 60 degrees. Here we can write down that theta equals to 60 degrees. So this was the first method. In the next step, I will present to you how to find out the size of angle theta according to the second method. In the second method, we will define angle ACB as alpha as we did in the first method. We know that I already explained to you that in the right angle ABC, if this angle equals to theta, then this angle must be equal to 90 degrees minus theta. That is to say, we know that alpha equals to 90 degrees minus theta. We will add theta to this equation and we will subtract alpha, and we will get that theta equals to 90 degrees minus alpha. Yeah. Okay, theta equals to 90 degrees minus alpha. And we will define AE as A as we did in the first method. EC is also equals to A. We will focus on the right triangle ABC. So I will copy again the right triangle ABC. And we will focus on this right triangle. AC equals to A plus A, that is 2A. BC equals to 6. I copied the right triangle ABC in this new page. And here it is very easy to see that in the right triangle ABC, cosine alpha equals to BC over AC. BC equals to 6, AC equals to 2A. Here we will divide both the numerator and the denominator of this side of equation number 1 by 2, and we get that 6 over 2 is 3, and 2 over 2 is 1. So in conclusion, we found out that according to equation number 1, cosine alpha equals to 3 over A. Here we will multiply equation number 1 by A, and then we will divide it by cosine alpha, and we will get that according to equation number 1, A equals to 3 over cosine alpha. Okay? A equals to 3 over cosine alpha. In the next step, we will focus on the right triangle DEC. So I will copy the right triangle DEC in the new page. So this is the right triangle EDC that I copied from the original drawing. EC equals to A, ED equals to 2. So in the right triangle EDC, what is the value of tangents alpha? Here tangents alpha is equal to ED over EC. ED is A, EC, ED is 2, ED is, here it is 2, and EC is A. So in conclusion, we found out that according to equation number 2, tangents alpha equals to 2 over A. But according to equation number 1, we've already found out that A equals to 3 over cosine alpha. Now we can substitute A in equation number 2 by 3 over cosine alpha. We will do it now and we will get that according to equation number 2, tangents alpha equals to 2 over A, and A according to equation number 1 equals to 3 over cosine alpha. So in conclusion, we found out that according to equation number 2, tangents alpha equals to 2 times cosine alpha over 3. We know that sinus alpha equals to cosine, tangents alpha equals to sinus alpha over cosine alpha. So we substitute tangents alpha in this equation number 2 by sinus alpha over cosinus alpha. And we get the tangents alpha, it is equal to sinus alpha over cosine alpha. And it is equal to 2 times cosine alpha over 3. Here we'll cross multiply this equation number 2, and we get that according to equation number 2, 3 times sinus alpha equals to 2 times cosine square alpha. Okay, this is equation number 2. We actually have the trigonometric identity that sinus alpha square plus cosine alpha square equals to 1. sinus alpha square plus cosine square, sinus square alpha plus cosine square alpha equals to 1. Here we will subtract sine square alpha from this trigonometric identity, and we will get that cosine square alpha is equal to 1 minus sine square alpha. That is to say, we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We'll do it now, and we'll get that according to equation number 2, three times sinus alpha equals to 2 times cosinus square alpha, and cosinus square alpha according to this trigonometric identity equals to 1 minus sine square alpha, so we'll substitute cosine square alpha in the equation number 2 by 1 minus sine square alpha. 1 minus sinus square alpha and we'll get that 3 times sinus alpha equals to 2 times 1 is 2. 2 times minus sinus square alpha is minus 2 sinus square alpha. So we'll add 2 sine square alpha to this equation, equation number 2, and we'll get that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. We'll subtract 2 from this equation, equation number 2, and we'll get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have a quadratic equation, and we'll find out the value of the variable sinus alpha according to the following formula, that x equals to minus b plus minus square root of b squared plus 4 times ac over 2a in our specific quadratic equation. The coefficient a equals to 2, the coefficient b equals to 3, and the coefficient c equals to minus 2. And the variable that we are looking for, that is to say x, it is equals to sinus alpha. So we put the data inside the formula for x, and we find out the value of the values of sinus alpha, because x equals to sinus alpha. We get that sinus alpha equals to minus b. B is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 2 times c, that is minus 2, over 2a. A is 2, so 2a is 2 times 2, that is 4. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus. Here, minus 4 times 2 is minus 8. Minus 8 times minus 2 is plus 16. And plus 16 plus 9 is 25. So inside the root we have only left with 25 over 4. So sinus alpha equals to minus 3 plus minus square root of 25 is 5. over 4. So here we will have two solutions that are possible for sinus alpha. The first solution will be equal to sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8. Minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2. Sinus alpha equals to minus 2. But because of the fact that the values that the function sinus alpha can accept, they are ranging from minus 1 to plus 1, and minus 2 exceeds this range of values that sinus alpha can receive, can accept. Therefore, this is incorrect answer. That is to say, sinus alpha can never be equal to minus 2, because the range of values that sinus alpha can be equal, there it is from minus 1 to plus 1, and minus 2 is less than minus 1. So this answer is the correct answer, and we left only with the solution that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. Sinus alpha equals to 1 over 2. If sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. And we have already found out that alpha equals to 90 degrees minus theta. Here alpha equals to 90 degrees minus theta. And here we found out that alpha equals to 30 degrees, so we substitute alpha by 30 degrees, and we get that 30 degrees equals to 90 degrees minus theta. We will add theta to this equation and we subtract alpha, and we get that theta equals to 90 degrees minus 30 degrees, that is 60 degrees. So in the second method, we found out that the size of angle theta is equal to 60 degrees. Okay, angle theta equals to 60 degrees. We finished with the second method. In the next step, I will summarize the lecture. Okay. We'll start with the first question. So in the drawing, we have a semicircle that is inscribed by a quarter circle. We know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. Okay? So here we define the center of the semicircle as point C, and then I presented to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. What is the meaning of rule number 1? Here we have tangent AB is tangent to this circle is point M. Point M is the point of tangency. And we have the radius OM that is drawn to the point of tangency, and whenever a radius is drawn to the point of tangency, then the tangent will be perpendicular to this radius. That is to say, AB will be perpendicular to the radius MO. AB perpendicular to MO or M, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees. We implemented rule number 1 in our drawing. Here we connected point C and B together by a straight line. CB is the radius of the semicircle that is drawn to the point of tendency, that is to say the radius CB is drawn to the point B, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent AO will be perpendicular to the radius BC. AO is perpendicular to BC, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Likewise, we connected point C and D together by a straight line. CD is the radius of this semicircle. The radius CD of the semicircle is drawn to the point of tendency, that is to say it is drawn to point D. This point, that is the point of tendency of tangent OH with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, tangent OH will be perpendicular to the radius CD. So OH is perpendicular to CD, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees. And because of the fact that AO edge is a quarter circle, this angle BOD must be equal to 90 degrees. So actually inside quadrilateral BCOD we have 3 right angles. Okay, inside quadrilateral BCOD we have 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the 4th angle, that is actually angle BCD. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation, and we got that the missing angle BCD equals to 360 degrees minus 270 degrees, it is 90 degrees. This angle equals to 90 degrees, so inside quadrilateral BCOD we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle. So quadrilateral BCOD is a rectangle. Okay, and then we have rule number 2, that the opposite sides of a rectangle are equal to each other. So in rectangle BCOD, the opposite sides of this rectangle BCOD are equal to each other. That is to say BC equals to OD. According to rule number 2, BC equals to OD, but BC equals to R, it is the radius of the semicircle. So R equals to BC equals to OD. From this equation we get that OD is also equals to R. OD equals to R, here OD equals to R. Likewise, CD must be equal to BO according to rule number 2, that the opposite sides of a rectangle are equal to each other. CD equals to BO according to rule number 2, but CD equals to, here, CD equals to R. This is the radius of the semicircle. So from this equation, CD CD equals to BD equals to R, CD equals to BO equals to R, here CD equals to BO equals to R, we derive that BO is also equals to R. BO, here, BO is also equals to R. So we found out that all the sides of quadrilateral BCOD are equal to each other and all of its angles are equal to 90 degrees. Therefore, we can conclude from it that quadrilateral BCOD is a square. Quadrilateral BCOD is a square. Then we connected points O and C together by a straight line, and OC is the diagonal of square BCOD. In order to find out the length of diagonal OC, we implemented the Pythagoras theorem on the great right triangle ODC. In this right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say OC square equals to OD square plus CD square. Again, in the right triangle OCD, according to the Pythagoras theorem, OC square equals to CD square plus OD square. OC square is the missing variable, CD equals to R, CD equals to R, and OD also equals to R. CD equals to R, so CD square is R square, OD equals to R, so OD square is R square. In conclusion, we found out that OC equals to R square plus R square plus R square is 2R square. In conclusion, we found out that OC square equals to 2R square. We took the root of this equation, and we found out that OC equals to the square root of 2 times R. So we found out that the length of diagonal OC is square root of 2 times R. Then we extended diagonal OC by a straight line until it touches the circle at point S. Point S is the touching point between the extended line segment OC and the circle. What is the value of line segment CS? This small line segment. CS will be equal to OS minus OC. It is very simple to see that CS equals to OS minus OC. Okay, CS or SC equals to OS minus OC. OS, what is the value of OS? O is the center of the circle. S is a point on the circle itself. This is exactly the definition of radius. It starts from the center of the circle and ends at any point on the circle itself. Therefore, OS is the radius of this circle that is equal to 3 units according to what is given as the question. So OS equals to 3 units. And OC equals to square root of 2R. So in conclusion, OS equals to 3 and OC equals to square root of 2R. Therefore, SC equals to 3 minus square root of 2R. The value of line segment SC is 3 minus square root of 2R. Then we completed the quarter circle to a circle. And we extended SO, we extended the diagonal SO or CO, we extended the diagonal CO by a straight line until it touches the circle at point M. Point M is the point of tendency of the extended CO and the circle. What is the value of MO? MO is the radius of the circle because it starts from the center and ends at point M, that is the point of the circle itself. Therefore, MO is the radius of this circle that is equal to 3 units, according to what is given us as the question. Then I presented to you rule number 3. According to rule number 3, whenever we have two chords that intersect with each other inside a circle, like in this drawing, we have chord AB that intersects with chord CD at point O. The intersection point of chord AB with chord CD is at point O. Then the following relationship is true between their parts, between the parts of the chords. That is to say, AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, it is true in any circle, in any two chords that intersect with each other. We can implement rule number 3 in our drawing. Why? Because in our drawing we have chord MS, this chord that intersects with chord AG, with chord FG. Chord MS intersects with chord FG at point C. Point C is the intersection point between chord MS and chord FG. So according to rule number 3, we will get that MC times CS equals to FC times CG. Okay? MC times CS equals to FC times CG according to rule number 3. MC, what is the value of MC? Here, MC equals to 3 plus square root of 2R. Okay? MC equals to 3 plus square root of 2R. What is the value of CS? We have already found out that CS equals to 3 minus square root of 2R. CS equals to 3 minus square root of 2R. And it is equal to FC. FC is R. And times CG, that is also R. Why FC is the radius of the semicircle? Because of the fact that it starts from the center of the semicircle and ends at point F, that is a point of the semicircle itself. For the same reason, CG is also the radius of the semicircle. That is to say, it is equal to R. So both of those two line segments, they are equal to R because they are the radiuses or the radii of the semicircle. Therefore, FC times CG equals to R times R, that is R squared. So we have this expression 3 plus square root of 2R times 3 minus square root of 2R, and it is equal to R squared. We found out the value of this expression by using the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to 3 and B equals to square root of 2R. Therefore, A squared will be equal to 3 squared. Minus B squared, it is minus B, that is square root of 2R squared. Square root of 2 squared is 2 times R squared. So in conclusion, we found out that the value of this expression equals to 9 minus 2R squared. 9 minus 2R squared equals to R squared. We added 2R squared to this equation, and we found out that 9 equals to R squared plus 2R squared is 3R squared. We divided this equation by 3, and we found out that R squared equals to 9 over 3, that is 3. And the area of the semicircle equals to half of the area of the circle. The area of the circle is pi R squared. Therefore, the area of the semicircle will be equal to half of it. That is to say, it will be equal to pi R squared over 2. So it is pi times R squared. R squared is 3, so we substitute R squared by 3. And we get that the area of the semicircle equals to 3 pi over 2 square units. Or in terms of numbers, it is equal to 4.71 square units. We finished with the first method. So the area of this semicircle equals to either 2 pi over 3 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first method. In the next step, I will present to you how we found out the area of the semicircle according to the second method. In the second method, we used all the things that we have already found out in the first method. We have already found out that BCOD is a square, and we have already found out that the diagonal OC equals to square root of 2R. And here we made the construction. We joined points O and F together by a straight line. What is the value of OF? O is the center of the circle, or the quarter circle. F is the point of the quarter circle itself. So OF is the radius, because this is exactly the definition of a radius. OF is the radius of the quarter circle, that is to say it equals to 3 units. Then we join points O and G together by a straight line. For the same reason, OG is the radius of the quarter circle, that is equal to 3 units. Therefore, triangle FOG is an isosceles triangle. Why? Because it has two sides that are equal to each other. FO equals to FG equals to 3 units. And in this isosceles triangle FOG, FC is the base of the isosceles triangle FOG, and OC is the median to the base FG. Why? Because it bisects the base to two equal parts. That is to say, it bisects the base to R and R. Okay, and we have rule number 4. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So here we have the isosceles triangle FOG. It is isosceles triangle because FO equals to OG equals to 3 units. And the base of the isosceles triangle FOG is FG, and the median to the base is OC. And according to rule number 4, the median to the base, that is to say OC in an isosceles triangle FOG, bisects is perpendicular to the base. That is to say OC is perpendicular to the base FG, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Okay, so really this is the implementation of rule number 4 in our drawing. Okay, so here we can see according to rule number 4, angle OCF equals to 90 degrees and the angle OCG will be also equal to 90 degrees. So here this angle equals 90 degrees and this angle equals 90 degrees. So then we focus on the right green triangle OFC. We know that OF equals to 3 units. We already found out that OC, the diagonal of the square, equals to square root of 2R, and FC equals to R. So we implemented the Pythagoras theorem on the right green triangle of OC. Okay. So this is the right triangle FOC. We implemented the Pythagoras theorem on this right triangle FOC. According to the Pythagoras theorem, the square of the apertures equals to the sum of the squares of the perpendiculars. That is to say, FO square equals to OC square plus AC square. Or FO square or F square equals to FC square plus OC square. OF equals to 3, so OF square is 3 squared, that is 9. Plus FC square. FC is R, so FC square is R square. Plus OC square. OC equals to square root of 2R, so square root of 2R square is 2R square. So in conclusion, we found out that 9 equals to R square plus 2R square. R square plus 2R square is 3R square. So 9 equals to 3R square. We divided this equation by 3 and we got that R square equals to 3. And we know that the area of the semicircle, the area of this semicircle equals to pi r square over 2, because it is half the area of the circle, and the area of the circle is pi r square. Therefore, the area of the semicircle that is half of it in its area will be equal to pi r square over 2. R square equals to 3, so we substitute R square equals to 3, so we substitute R square by 3, and we got that the area of the semicircle equals to 3 pi over 2. So the area of the semicircle equals to either 3 pi over 2 square units, so in terms of numbers, it is equal to 3.71 square units. Okay, so we finished with the second method, and in the next step, so we finished with the first question. In the next step, I will present to you the second question. How we solve the second question. We had two methods. And here we have in the drawing the right triangle ABC. Angle ABC equals to 90 degrees. And side BC of the right triangle ABC equals to 6 units. DF, line segment DE equals to 2 units. DE is perpendicular to AC, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees. And we want to find out the value of this angle BAC, that is equal to theta. Okay? So in order to find out the value of angle theta, we made a construction. From point E we drew perpendicular on BC. That is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. According to our construction, we defined the touching point between the perpendicular from point E and the side BC as F. Then we defined angle ACB as alpha, and because of the fact that in the right triangle ABC this angle equals to theta, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC, 280 degrees. If this angle equals to theta, this angle must be equal to 90 degrees minus theta. So in conclusion, we found out that because according to our definition this angle equals to alpha, we will derive from it that alpha equals to 90 degrees minus theta. So here alpha equals to 90 degrees minus theta. We added theta to this equation and then we subtracted alpha, and we got that theta equals to 90 degrees minus alpha. So what is here in this the right triangle EFC, this angle equals to alpha, this angle equals to 90, must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle to 180 degrees. But here 90 degrees minus alpha, it is theta, so we can write down that this is equal to theta. And it is given us the question that angle DEC equals to 90 degrees. It is a right angle, and angle FEC equals to theta. Therefore, the missing angle DEF, will be equal to 90 degrees minus this angle FEC. Angle DEF will be equal to angle DEF will be equal to angle DEC minus angle FEC. Angle DEF equals to angle DEC minus angle FEC. So angle DEF, the missing angle, equals to angle DEC, that is 90 degrees, minus angle FEC, that is 90 degrees minus theta. So in conclusion, we found out that angle DEF equals to 90 degrees minus 90 degrees minus alpha, because angle EFEC it is equal to 90 degrees minus alpha. Okay, so in conclusion, we found out that angle DEF equals to 90 degrees minus 90 degrees minus alpha. We opened the brackets here and we found out that the missing angle DEF equals to 90 degrees minus 90 degrees, that is 0, minus alpha is plus alpha. So in conclusion, we found out that the missing angle DEF equals to alpha. So in the right triangle DEF, if this angle equals to alpha, this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle to 180 degrees. So this angle equals to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to theta, so we can substitute 90 degrees minus alpha here by theta. We did it, and this angle equals to theta. Okay? Then we proved that the right triangle ABC is similar to the right triangle FEC. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to 90 degrees. Those two angles are also equal to each other, they are both equal to theta. And here, those two, I repeat again, we will prove that the right triangle ABC is similar to the right triangle FEC. The right triangle ABC is similar to the right triangle FEC, this right triangle. Why they are similar to each other? First of all, those two angles, they are both equal to theta. those two angles, they are both equal to 90 degrees, and we have also a common angle that belongs to both triangles. This angle, angle alpha, belongs to triangle EFC. This angle, angle alpha, belongs also to triangle ABC. So this angle equals to itself. Therefore, we prove that all the angles of triangle ABC can go into all the angles of triangle EFC. Therefore, triangle ABC is similar to triangle FEC according to angle similarity rule. Okay? Triangle ABC is similar to triangle FEC according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over AC equals to FE over AC. AB over AC equals to FE over AC. So AB over AC. AC is A plus A is 2A over E, and it is equal to EF. EF is Y according to our definition over EC. EC equals to A. So in conclusion, we found out that AB over 2A equals to Y over A. We have A on both sides of the equation number 1, so A will get cancelled, and we left only with AB over 2, that is equal to Y. We multiplied this equation number 1 by 2, and we got that AB equals to 2Y. Here AB equals to 2Y. Then we proved that the right triangle ABC is similar to the right triangle EDF. Why those two right triangles are similar to each other? First of all, those two angles that are equal to each other, they are both equal to theta. Those two angles that are also equal to each other, they are both equal to 90 degrees. And those two angles that are also equal to each other, they are both equal to alpha, so we prove that all the angles of triangle ABC can go into all the angles of triangle EDF. Therefore, those two triangles can go into each other according to angle similarity rule. Triangle ABC is similar to triangle EDF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that AB over BC equals to DF over EF. AB over BC equals to DF over EF. AB equals to 2Y. BC equals to 2A. BC here, BC, it is equal to 6. So we substitute BC by 6. DF equals to X, and EF equals to Y. So in conclusion, we found out that 2Y over 6 equals to X over Y. We divided both the numerator and the denominator of this side of equation number 3 by 2, and we got that 2Y over 2 is Y, 6 over 2 is 3. So in conclusion, we found out that Y over 3 equals to X over Y. Because we multiplied this equation number 3, and we found out that Y squared equals to 3X. But here, in this right triangle EDF, we know that according to the Pythagoras theorem, X squared plus Y squared equals to 2 squared. That is to say, X squared plus Y squared equals to 4. So according to equation number 2, we've only found out that X squared plus Y squared equals to 4. Now we can substitute Y squared in equation number 2 here by 3X, because Y squared equals to 3X. We did it, and we got that according to equation number 2, X squared plus Y squared, that is 3X, equals to 4. So we subtracted 4 from this equation, and we got that X squared plus 3X minus 4 equals to 0. And we have this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the formula, that x equals to minus b plus minus square root of b squared over 2a. In our specific quadratic equation, a equals to 1, b equals to 3, and c equals to minus 4, and x is the variable that we are looking for, so we put the data inside this equation and we got that x equals to minus b equals to 3, so minus b is minus 3, plus minus b squared. B is 3, so b squared is 3 squared, it is 9, minus 4 times a is 1 and c is minus 4, so it is minus 4 times minus 4 over 2a. A is 1, so 2 times 1 is 2. So in conclusion, we found out that x squared equals to minus 3 plus minus square root of 9 minus 4 times minus 4 over 2. Here, minus 4 times minus 4 is plus 16, and plus 16 plus 9 is 25. So inside the root, we have left only with 25. So in conclusion, we found out that x equals to minus 3 plus minus square root of 25 over 2. The square root of 25 is 5. So in conclusion, we found out that x equals to minus 3 plus minus the square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8. Minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. But because of the fact that x is a length, x is the length of side df of the right triangle EDF, therefore it must be a positive number, so x cannot be a negative number. Therefore we cancel this solution and we left only with the solution that x equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2 and 2 over 2 is 1. So we found out that x equals to 1. So we copied the right triangle EDF from this original drawing. X equals to 1, ED equals to 2, it is given us in the question, EF equals to y. So here, and we know that this is the missing angle that we are looking for, theta. Here, cosine theta equals to df over ed. Cosine theta equals to df over de. So df equals to 1 and d equals to 2. So in conclusion, we found out that cosine theta equals to 1 over 2. And if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. So we found out that the value of angle theta, the size of angle theta, is equal to 90 degrees. We finished with the first method. In the next step, I presented to you how to find out the value of angle theta according to the second method. Here we defined this angle as angle alpha. So here we focus on the right triangle ABC. In the right triangle ABC, this angle equals to alpha. AC equals to, according to the first method, we defined this side as A, and this is also A, because they are equal to each other. Therefore, AC, the hypotenuse, equals to A plus A, that is 2A. AC equals to 2A. BC equals to 6 units, it is given us the question, and we defined angle ACB as alpha. So here, cosine alpha will be equal to BC over AC. Cosine alpha equals to BC over AC. BC is 6 and AC is 2A. So in conclusion, we found out that cosine alpha equals to 6 over 2A. We divided both the numerator and the denominator of this on this side of the equation by 2. 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that cosine alpha, according to equation number 1, equals to 3 over A. Here we multiplied this equation by A and then we divided by cosine alpha, and we found out that A equals to 3 over cosine alpha. Then we focused on the right triangle CDE. In the right triangle CDE, we know that here EC equals to A according to our definition, ED equals to 2 according to what is given as the question, and this is angle alpha according to our definition. So here tangent alpha will be equal to ED over EC. Tangent alpha equals to ED over EC, ED equals to 2 and EC equals to A. So in conclusion, found out that according to equation number 2, tangent alpha equals to 2 over A. But according to equation number 1, we have already found out that A equals to 3 over cosine alpha. So we can substitute A by 3 over cosine alpha in equation number 2. We did it and we got that tangent alpha equals to 2 over A, but A equals to 3 over cosine alpha. So here we substitute A by 3 over cosine alpha, and we got that tangent alpha equals to 2 times cosine alpha over 3. Tangent alpha is sinus alpha over cosinus alpha, so we substitute tangent alpha by sinus alpha over cosine alpha. So in conclusion, we found out that sinus alpha over cosine alpha equals to 2 sine cosine alpha over 3. We multiplied this equation and we found out that 3 times sinus alpha equals to 2 times cosine squared theta. Okay, then we have the trigonometric identity. According to the trigonometric identity, sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this trigonometric identity and we found out that cosine square alpha equals to 1 minus sine square alpha. Therefore, we can substitute cosine square alpha in this equation number 2 by 1 minus sine square alpha. We did it and we got that 3 sine alpha equals to 2, and this is cosine square alpha, that is 1 minus sine square alpha. So we got that 3 sine square alpha, we open the brackets here, equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 times sine square alpha. We added 2 sine square alpha to this equation and we got that 2 sine square alpha plus 3 sine alpha equals to 2. We subtracted 2 from this equation and we got that quadratic equation that 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So we have here a quadratic equation. The missing variable is sine alpha, and the solution to the quadratic equation will be according to the formula for x, that x equals to minus b plus minus square root of b square minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 2, the coefficient b equals to 3, and the coefficient c equals to minus 2. We put the data inside the equation for x and we found out the value or the values of sinus alpha because x equals to sinus alpha. So we got that sinus alpha equals to minus b equals to 3, so minus b is minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9, minus 4 times a. A is 2, so it is minus 4 times 2, minus c, that is minus 2. So this expression is minus 4 times 2 times minus 2 over 2a. A is 2, so 2 times 2 is 4. So here sinus alpha equals to minus 3, and inside the root we have minus 4 times minus 2 is minus 8. Minus 8 times minus 2 is plus 16. Plus 16 plus 9 is plus 25. So inside the root what is left, it is only 25. So sinus alpha equals to minus 3 plus minus square root of 25 over 2. The square root of 25 is 5. So in conclusion we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we have two solutions that are possible for sinus alpha. The first solution is sinus alpha equals to minus 3 minus 5, that is minus 8 over 4. Minus 8 over 4 is minus 2. So sinus alpha equals to minus 2. But because of the fact that the values that the function sinus can accept is ranging from minus 1 to plus 1, and minus 2 exceeds this range, because minus 1 is less than, because minus 2 is less than minus 1, therefore this solution is incorrect solution. That is to say, sinus alpha can never be equal to minus 2, because the range of values that sinus alpha can accept is between minus 1 to plus 1. And minus 2 is not inside this range, therefore this solution is incorrect solution. Okay, and we're left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2, and if sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. And we have already found out here that alpha equals to 90 degrees minus theta. So here alpha equals to 90 degrees minus theta. Here we just right now found out that alpha equals to 30 degrees, so we can substitute alpha by 30 degrees. So we did it, and we got that 30 equals to 90 degrees minus theta. We added theta to this equation and we subtracted 30 degrees, and in conclusion we found out that theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees is 60 degrees. So in conclusion we found out that the size of angle theta is equal to 60 degrees. The size of this angle theta is equal to 60 degrees according to the second method also. Okay, thank you very much.